Hello everyone, hopefully you're doing well. In this video, we're going to start with chapter 5, exponents, polynomials, and polynomial functions. We already had a chance to go over linear equations. Of course, they are very important for solving problems, but they are not sufficient. However, to solve all problems, right? So many real-world phenomena are modeled by polynomials. All right. So what we're gonna do in this chapter, that's why we begin this chapter by reviewing exponents, and we will then study operations on polynomials and how polynomials can be used to solve problems. Let's begin with exponents and then eventually talk about scientific notation. So we call that exponents may be used to write repeated factors. For examples, when we said repeated factors, if I have 2 times 2 times 2 times 2 times 2, I have I have 5 factors that's the same, it's 2. So I can say it's 2. How many times you see 2 here? 1, 2, 3, 4, 5. So we're gonna say 5 power 2. So as we said, exponents may be used to write repeated factors in a more compact form. Okay, exponent can also be used when the repeated factor is a number or a variable. So we can, here I give you numbers, but let's say if I have x times x times x, how many x you see here? We see x 3 times. But then what are the objectives of this section? First of all, what we're going to do is to use the product rule for exponents. We're going to evaluate expressions raised to 0 power and use the quotient rule for exponents, evaluate expressions raised to the negative nth power, simplify exponential expressions with variable in the exponents. And we're going to convert scientific notation. I said notation is in standard notation. So let's start with the first objective, which is the use of the product rule for exponents. So what's exponent exactly? If m and n are positive numbers, okay, so that's what we're gonna do in terms of exponents rule. Exponents that are natural numbers are shorthand notation for repeated factors. As you can see here, having 3 power 4, that means we have 4 factors of 3. So 3 is the base, and 4 is the exponent that we call power. Like if we have a power n, that means I use n because I don't know what the exponent would be. We're gonna consider a as the base, and we're gonna consider a as the base and n as the exponent or the power. So that's what we're planning on doing. Note that by the order of operation, that exponents are calculated before the order of operations. Remember when we do PEMDAS, PEMDAS. So after you do parentheses, you know, after parentheses, let's say exponents come second. So then you use the order operations, multiplication, divisions, addition, and subtraction. So what's the product rule? The product rule, we're gonna say, talk about the product rule. If m and n are integers and a is a real number, then a time power m times a power n equal a power m plus n. So what we mean by that, in other words, the product of exponential expressions with a common base is a common base raised to the power equal to the sum of the exponent of the factors. Let's say if I have x power 7 and times x power 6. Now, because the bases are the same, I have x as base, I can just add the exponent. So now I have x power 13. Now, if I have a power times a power 4, remember there is one here that I never write. So a power 1. So what we're gonna do, it would be a1 plus 4, so it would be a power 5. Now, if I have x power 6 times y power 3, you cannot add the exponent because the bases are different. So here, you would only rewrite it. This one cannot be simplified because the bases are totally different. Now, they give us a few examples here to do. For example, the access to you know, do the exponent 3 power 2 times 3 power 4. Because the exponents are the same, we can simply add, because the bases are the same, we can simply add the exponent. So it would be 3 power 6. And what you know from that is that we're going to have, 3 power 6 is 3 times 3 times 3 times 3 times 3 times 3. Is that 6 times? Then you use a calculator. That's going to give you 729, I believe, right? That will be 729 for this. Now, in the second examples here, you see we don't use numerical data values, but we use variables because z is the base. The same, all I need to do is add the exponents. So when I add the exponents, 3 plus 2 is 5 plus 5 is z power 10, and that's the best simplification we could do. Not all the time you're going to find only one variables or only one base that can be numericals. Sometimes we can combine like terms. For example, in the third examples, we see that 3 and 4 are real numbers. If I want, I can multiply 3 times negative 4 times y power 2 times y power 4. Remember distributive law in multiplications. So A times B is the same time doing B times A. So it doesn't matter in which order I put my factors, as long as they are factors. Remember, this is a multiplication sign. So 3 times negative 4 give us negative 12. Remember, in this case, we multiply the coefficients with coefficients and, factors with the same base, like y, we're going to add the exponent. So that will give us negative 12y power 6, and that's the best thing to do. Remember, the power 4, the power 3, 2 you see here, the power 2 is only for y, and the power 4 is only for y. It doesn't affect the 2, the 3, and the negative 4. Zero exponents. We would say like the definition of a power n does not include the possibility that n might be zero. But if it did, then the product rules, would be, for example, let's say you do a power 0 times a power 1, power 2. I'm gonna put a clear 2. Power 2, then it would be a 0 plus 2, as you can see, is power 2. That means any number any number power 0 is equal to 1. So if a, from this we can reasonably define that a power 0 equal 1 as long as a does not equal to 0. Remember, you cannot say 0 power 0 is equal to 1. That doesn't, it's indeterminate form. But here, a power 0, 5 power 0 is 1, negative 16 power 0 is 1. All right. So, now if we have negative 5 power 0 is negative 1. Remember, that negative in front doesn't affect it. That's why I do 1 with parentheses, 1 without parentheses. So very important. We can do even a few examples. Remember here, 5 power 0 is 1, we already said. Any expressions power 0 is 1, because if you try to distribute, we're going to do x power 0 times y power 0 times z power 3 power 0. So that would be definitely 0, 1. Sorry, I said 0, that's 1. So that would be x power 1 is 1, y power 1 is 1, z power 1. So that would be 1. Yeah, definitely. Any expression power 0, as long as x, y, z are not, none of them are 0. So they should be non-zeros. Now, as we said, if you have this one, it's like you have x power 0. You see the negative is outside, is 1, right? So that gives you negative 1. Okay. Now, the quotient rule, because we're trying to go a little bit better, because we're going to use the quotient rule for exponents, what we said about quotient rule, because we need to use that to find quotients of exponential expressions, we need to understand some basic properties of quotient rules. So if a is a non-zero real number and m and n are integers, remember a cannot be zero, now we can subtract the exponent. Remember when in multiplication, a power m times a power n, you add the exponent, keep the base, but if you have a power m over a power n, the first thing you double check it's about the bases. There is this is the bases are the same, exponent are different. We're going just to subtract the exponent. So that's what we do here. We subtract the exponent. For example, if we have x power 7 over x power 3, we can do x power 7 minus 3. That gives you x power 4. If I have x power 7 times x power 3, that would be x power 7 plus 3, x power 10. So remember, multiplication and divisions have a different properties. With some examples, we can explain this. Base is the same, we subtract the exponent, so 6 power 8, okay? If we see here, base is the same, y 6 minus 2, so we're going to have y power 4. Now, remember, we can simplify real numbers with real numbers, variables with variables. First of all, I feel like I can do 36 over 9 times x power 5 minus 1. Remember, there is a 1 here we don't see. So it's end up 36 divided by 9 is 4x power 4. Because remember, we need to subtract. Now, again, we combine real numbers with real numbers. 10 divided by 15 times a 7 minus 5 times b 9 minus 9. So what happened with 10 divided by 15? Common factor is what? Yes, it's 5. So 10 divided by 5 is 2. 15 divided by 5 is 3. Now we're done with this. A power 7 minus 5 is a square. Okay. And now, remember we have b. This one is times 1 because b power 0, we're going to have b power 0. That would be 2a squared times 1 over 3. That would be 2a squared over 3. Yeah, we're gonna try to do as many examples as possible, but because we have many objectives to follow, we're going to do objective 4 where we would simplify expressions with raised to negative power. Okay, simplify expressions raised to negative power when the exponent of the denominator is larger than the exponent of the numerator. We apply the quotient rule, yields a negative exponent. So let's say what you see, if we have a power negative 2, we can do 1 over a power 2. The same way, if I have 5 power 2 is 25. Negative 5 power 2 is negative 25. Negative 5 power 2 is positive 25. You see, the second one is negative because we don't have a parenthesis with that. Now, if you look at this one, 5 power negative 2, you cannot talk about 25 because if you try to enter this in a calculator, it's gonna say 1. So that would be 1 over 25 because the exponent cannot be negative. A few examples to explain this better. The first thing to do is to see 3 power negative 2 is 1 over 3 power 2, so 1 over 9. 1 over x power 7. And remember, the 2 will remain in the top. The x power 4 would go in the denominator. Really, you need to remember that without parentheses, x is the base for the exponent negative 4, not the 2x. So the 2 is not in it. So we're going to leave the 2 on the top. Something very good. We can continue to do more examples of these. We said that simplifying right using positive exponent. The first thing is negative 1 times x power negative 3. So we're going to have negative 1 over x power 3. Simple, right? And here we're going to have negative 1 times 3 power negative 2, negative 1 over 3 power 2. That's give you negative 1 over 9. Okay? And the last one, you see that negative 3 has a parenthesis. That means we need to flip it. We're going to have negative 3 power 2. So that would be 1 over 9. So you need to notice the difference in the result when the parentheses are included around the negative 3. Another examples to give you an idea, simplify and rewrite in positive. Now, we had numerators and we try to jump it to the denominator. Now, the negative is in the denominator. We need to jump it to the numerator to make it possible, like 1 times x power 3. So that will be x power 3. Now, the problem, I'm going to flip y to be on the numerator and x to be in the denominator. We can do that with no problem. Notice that to convert a power with a negative exponent to 1 with the positive exponent, you simply switch the power from a numerator to a denominator or vice versa and switch the exponent to its positive value. So we can do that, of course, all the time. So if they ask you to do all of this, okay, there would be no problem with that. We have more examples because in these examples, it would be a little bit different. If you look at A, we have M 5 minus 15. That would be M negative 10. Now you really need to flip it to make it 1 over M power 10. B, I believe, is the same. 4, 2 minus 5. 4 power negative 3. The exponent should never be negative. You need to jump it to the denominator. 1, 3 power 4. And I believe 3 power 4 would be 4 power 3. 4 times 4, 16 times 4, 64. So 1 over 64. Here we see that we're going to have its multiplication. That means we have negative 10 plus 3 y power negative 7 that you can rewrite as 1 over y power 7. Yeah, we did it. We are doing it correct. Now look at this one. If we have q5 minus negative 4, you see, in multiplication, two negative become positive. So we're going to have q5 plus 4 should be q9. Yeah, I don't know if you're okay with that examples, but we're gonna continue to do more just in case to make sure you get it. This one's a little bit longer. So first of all, you can rewrite it as 10 over 20. Now x negative 8 minus 1, because I bring the negative on the top, y 5 minus negative 5. 10 over 20, you only have 2 in the denominator. So we're going to have x power negative 9, y 5 plus 5 over 2. Remember? Because 10 divided by 20 is 1/2. Okay? Now, because x negative, because we're going to have x power negative 9, y 10 over 2. The exponent should never be negative. So what we do, we jump the x to the denominator and keep the y in the numerator. Voila. Voila. Okay. F, what we do with F, first of all, the exponent doesn't affect the coefficient. So if I remove it, I can still have x times x power negative 1 times x power 5 times x power 5, okay? So now we have x power 7. All right, look at that. We have 4x negative 1 plus 5 over x power 7. 4x power 4 over x power 7. Now, the problem, we have x as the base, so we're going to have x power 4 minus 7. That gives us x power 4x power negative 3. Now we have 4 over x power 3. Why that? Because we cannot keep the exponent negative. If it's negative in the numerator, we're going to jump it to the denominator to make it positive. If it's negative in the denominator, we would jump it in the numerator to make it positive. We have more examples for this one. All again, simplify, assume that a and t are non-zero, because sometimes with zero, that would be a problem, right? What they ask you to do here is still same base. Remember, this is multiplication. So if I have the same base, I can simply add the exponent. And right here, there is nothing I can do because they said 2a plus 3. We cannot add these two to make it 5a because the a is a variable. We don't know what it is. The same way here in the divisions, we said we subtract the numerator, the denominator from the numerator. So t minus 5. That's the rules. See, you subtract the exponent in the denominator from the exponent in the numerator. Then from here, we can distribute t minus 1 minus t plus 5. X equal t plus 4. And probably that's the final answer for this. Yay, final answer. Yeah, so many operations you can do on exponents. Exponents is giantly important. But we're gonna talk about something probably you are aware of. It's scientific notation, because very large and very small occurring frequency in nature. So we have numbers that are so big we don't have enough space to store it. And the same way we have numbers that are so small, like 0.0000000 something, like the distance between the Earth and the sun is approximately 150 million kilometers, right? So it would be, it's a big number. We don't want to write that one. Using the scientific notation, we can rewrite it more in a simplest form. A helium atom has a diameter of 0.000002226 centimeter. So we said it would be better that we use scientific notation to write the very large number or the very small number. That will be convenient for all of us. So in many fields of scientific or science, we encounter very large or very small numbers. So scientific notation is a convenient way for shorthand for expressing these type of numbers. So a positive number is written in scientific notation if it is written as a product of a number A, where A is one, can be one up to 9 point something, but never 10. So you can do 1 point something or 9 point something, but never 2 digits. Okay. And an integer R, that is the exponent. So usually we said it's A times, I mean, A is a number, right? It's a decimal number times 10 power R. R is the exponent. So when we write when we write a number in scientific notation, there are some rules we can follow. The first rules is like we move the decimal point in the original number until the new number has a value between 1 and 10, right? We cannot, let's say, for example, if you have 120, I mean, 1,200, you cannot do 10 times 12 times 10 power 2 because 12 is not a number between, it's not a digit between 1 and 10, okay? From 1 to 9 point something. So what we can do is move out in 1, that means 10, 1.2 times 10 power what? Yes, 3 digits. So that's the second rule. So count the number of decimal places the decimal point was moved in septo. If the original number is 10 or greater, the count is positive. If the original number is less than 1, the count is negative. Write the product of the new number in step 1 by 10 raised to an exponent equal to the count found in step 2. For example, here, first of all, I want to make sure I rewrite it only one digit, 7.4. So how many places I move? 1, 2, and 3. That's 3 moves, right? So that means it's 10 power 3. Now it's the same here. I see 7.4. You see, I don't even think. I'm not going to write 47. I only need to write 4.7. Now look, if we go 1, 2, 3, and 4. Obviously, you can see this because we can use that point. So in the first one, what you see, we move the decimal places to the left. Okay, we go from right to left so that the new number has a value between 1 and 10. Since we moved the decimal 3 places, the original number was greater than 10. Our count is positive 10, 3. Sorry, that's why you see we write it 10 power 3 for here. But in the second one, we move the decimal 4 places, okay, to the right so that the new number has a value between 1 and 10, so which is 4.7. Since we moved the original decimal 4 places and the original number was less than 1, our count, how many counts you have? 1, 2, 3, and 4. 10 power what? Oh yeah, exponent negative 10 power 4, negative 4. Okay? 10 power negative 4. So that will be the answer for that one right there. All right. So many things we can do. In general, what you need to remember, in general, to write a scientific notation, in standard form, move the decimal point the same number of space as the exponent on 10. If the exponent is positive, move the decimal point to the right. If the exponent is negative, we move the decimal point to the left. And last examples in this section, you see, write each of the following in standard. Remember, in these examples, we write in scientific notation. That means uh, something times 10 power something. So that's scientific notation. In this example, they give you the scientific notation and ask you to write in standard form. The exponent is 3. Since the exponent is a positive 3, it's not 3, it's positive 3, we're going to move the decimal point 3 units to the right. So the new decimal point would be somewhere here. So it's 5273.8. Okay? We move the decimal 3 places to the right. Now, look at the second one. Since first of all, we see -5. -5 means we're going to move 5 units to the left. Since the exponent is negative, we're going to do 1, 2, 3, 4, and 5. So that means it's a 0, 0, 0, and 0. So we're gonna have 0.40. 645. See, I put everything. I hope this first sections in chapter 5, exponents, polynomials, and polynomial functions are helpful in a different video. Of course, we're going to come back for more work with exponents and scientific notation. Let me know if you have any questions. I'll see you in a different video. Take care.